Now, understanding the Bronsted Lowry and connection with the conjugate acids and base identification in any types of reaction, mainly acid and bases, we usually focus on first how can we determine which one is the acid and which one is actually the conjugate base pair with that acid. And Bronsted Lowry actually were able to bring this particular understanding to fruition by first for acids. We do know that in this case an acid must be a proton donor. I'll just put it as D. And while for the base on the other hand must be a proton acceptor. So this is kind of a transition from the Arrhenius understanding, which is more about any acid must contain a proton and a base must contain a OH, but this wasn't actually applicable to the idea of ammonia. And ammonia, we do know, is actually NH3 and it doesn't have a OH. So that being said, it's kind of really a nice way of transitioning from Arrhenius over to the Bronsted Lowry, and later down the road when you head into undergrad there are other exceptions and then you will know more about Lewis electron idea. Now in this video the big idea is to actually keep track two properties that govern which ones are the conjugates, acid or base pairs based on a specific question. One is the change in the number of the hydrogen atom present in a particular compound in a given question. Let's say for example we have a particular compound with the letter H and there is some kind of I would say polyatomic ion right there. What we notice is that the number of hydrogens and how the number changes either by increasing or decreasing tells you or gives you a little bit of an insight on what the conjugate is, either as an acid or a base. Now the next idea to take note of is that changes in the oxidation number of the polyatomic ion, that is not hydroxide, will also give you an indication of what is happening, because that corresponds to the hydrogen atom present in that particular compound. So we said that triangle in here is actually the polyatomic ion, and this polyatomic ion usually has a charge in here. Increase or increase in the charge tells you whether it's actually heading towards the conjugate acid or conjugate base pair based on the reactant side. So for this case there is a little bit of an info in the conjugate acid compared to that of the conjugate base, and this trend line which heads towards more conjugate acid tells us that first there is an increase in the oxidation number of our polyatomic ion. I'll just put it as an ion. So if the oxidation number increases, that leads towards conjugate acid. If the polyatomic ion's oxidation number decreases, it heads towards the conjugate base. In reflection, this actually is translated into an increase in the hydrogen atom number present in that particular product. So if there is an increase in the number of hydrogen atom present in that particular product, then it actually tells us that yes, it is a conjugate acid. If there is a decrease, then it tells us that we are actually creating a conjugate base. So now these big ideas and information is out of the way, let's work with a specific example right here, which is a phosphoric acid spectrum. Now we do know that phosphoric acid is actually known to be H3PO4, and let's go with decreasing in the number of hydrogen atoms right there. So we're going to go to H2. That results in the charge of phosphate to be -1, and the next one here is H with a phosphate charge of -2, and finally we have phosphate with a charge of -3. So now this is actually the spectrum. We'll label this as 1, 2, 3, 4. We can be able to determine based on which is the conjugate acid or conjugate base. Let's start, for example, let's say number 3 right there. If you look at number 3, if we go from right to left, based on the screen, we head towards a conjugate acid approach because you're seeing an increase in the protons, but at the same time there's an increase in the polyatomic ions charge right there, going from -2 to 0, while on the other side, which is going from left to right, we actually head to a conjugate base, which is just one conjugate base based on number 3. Now if you go for number 2, which is starting here, and we're given number 2, we are asked to find the conjugate acid. The conjugate acid tells us that, hey, we are heading to number 1 only, which has an added proton with a 0 charge on that particular polyatomic anion right there, while on the other side, if we remove a hydrogen, we're causing the formation of a conjugate base 3, and if we remove another hydrogen, we actually create another conjugate base right there, which is just phosphate. And then finally, number 1, you can try that yourselves, and you guys can actually determine what the conjugate acid is and the conjugate base. You can put your answers in the comment section below. And now that's out of the way, we're going to go into example 2, which is what is the conjugate acid and conjugate base of this particular compound right there. Now this compound, which is known to be HCO3 with a charge of 1-, actually first, to get a conjugate acid, we need to do something, which is to be able to gain a proton. So if we gain a proton right here, H+, what happens is that we actually form a product which is actually H2CO3 with a 0 charge, because 1 plus minus 1, it's actually equals to 0. As a result of that, we also notice that the anion right here has a charge that actually increases from -1 to 0. So now this is out of the way, let's go into the other side right here to get the conjugate base. And to get our conjugate base, what we know is that we actually need to lose a particular proton. So once we lose a proton, what we actually get as a result is just a carbonate with a charge of 2-. And what that results in is that there is a decrease in the anion's charge that causes our result to generate a conjugate base, while on this side here is actually the formation of a conjugate acid of this particular compound given right there. Now in here we notice that in this case, this particular compound right here, we're going to represent as P in this direction, actually acts as a base, while on this other side here, heading towards a conjugate base, it actually acts as an acid by losing a proton. So I'll give you guys a little bit of a challenge question. You can answer that in the comment section below, and the challenge question is, what is a conjugate acid and conjugate base of ammonia? You can put that in the comment section and we can chat on future questions that you may have. All the same, stay smart and believe in yourselves.